Step 6 is to model open channel flow through our specific channel. Now that we have our max flow through the watershed, and that is our Q from the rational method or the QP from the SCS curve number method, we can model this in relation to our specific cross-section using Manning's equation for open channel flow. Manning's equation is once again an empirical equation. Q equals 1.486 over N times A times RH to the 2/3 times S to the 1/2. And this is for steady and uniform conditions. N is our roughness coefficient. S is our slope in foot per foot. A is the area of our flow. And RH is our hydraulic radius in feet, which is going to be our area of our flow divided by the wetted perimeter. Now we'll go through two methods, by hand and using software. And the software is going to be more common, but by hand kind of gives you an understanding of what the inputs to the software are. So let's take our example cross-section. It's usually a trapezoid, or we can estimate it as a trapezoid. The slope of the riverbed we can get from topography in the DWG file or from Google Earth. Our flow area we can get from the geometry of the cross-section, and it's going to be a function of depth. Our hydraulic radius we can get with our area again in our wetted perimeter, which is a function of the which is going to be, we can calculate with the geometric properties of the river cross-section, and we want that again as a function of depth. And then Manning's roughness coefficient, we can estimate using site media, and I'll once again post a table for that for you to look at for calculating or for grabbing Manning's roughness coefficient. Now, for mathematical analysis, we can use Manning's equation for open channel flow to solve for our normal depth under steady, uniform conditions. Remember, steady flow means conditions don't change over time, and uniform flow means conditions are the same across the channel. Now, I've written the example equations for a trapezoidal channel with flow depth y, bottom width b, top width of the flow t, and our slope z, slope of the side slopes, c. And we can plug this into Manning's equation and rearrange to then solve for y. After finding our normal depth, you can project this onto your river cross-section along with a factor of safety to predict or verify a high water line. In the next section, I'll talk about modeling. I'll talk about HECROS, the Hydrologic Engineering Center River Analysis Station. And that will be a text section so that you can see some better graphics, not my hand-drawn graphics, about what is going on and what is being produced by the HECROS model.